All right. I will get started. As soon as I get myself some markers here. So, let me begin with a word of prayer. So, Dear Heavenly Father, we thank you for this day. I thank you for these students, and I just pray you be with us, help us to glorify you what we do, and I just pray that we'd understand a little bit more about your creation together today, Lord. In your name I pray. Lord Jesus, amen. Let me start you on an example. So here's my example. Mr. Top Hat, again, no relation to Top Hat, right? Takes a ball, right? And throws it, all right? And at the top, he throws it how high? Let's suppose that he throws the ball a distance of, 100 meters. He throws it 100 meters upwards from where it left his hand. My question then is, what speed did he throw the ball? So suppose that it's thrown vertically like that, all right? By the time I get back to the board, you guys should have solved this. All right. How should I solve this? Any suggestions? What should I use? What should I not use? How about we don't do it the way I did it last time we asked this question, right? The last time I asked this question, right, what did I do? I measured the distance to the ceiling and some silly stuff like that. But, it's essentially that same question I started with, right? And the way we did it before was we used the kinematic equations, right, to do this. But we don't need to do that anymore, right? We have a better way. How will we do it? Yeah. Ooh, you hurt me with that. But no. Yes. Yeah, that was what I was fishing for. So let's use energy. Now, what you're saying is equivalent because the equations actually mean, like all those equations we looked at before, if you actually kind of tilt your head and squint and look at the timeless equation, the truth of the matter is that is energy conservation. So yeah, let's use conservation of energy because what's at work here is gravity, right? That's it. So what we can say is that the potential energy at the start plus the kinetic energy at the start is equal to the potential energy, let's see here, at the top, right? Plus the kinetic energy at the top, right? Which I'm just using 1 for apparently. So and then, one of the wonderful things about physics is we can make h equals to 0 wherever we want. So I chose to make h equals to 0 where he throws the ball from. So given that choice, what's the initial potential energy? 0. Yeah, 0, right? mg times 0. What's the initial kinetic energy? Well, I don't know. But it's 1/2 mv naught squared, right? And that's what I'm interested in figuring out. What is v naught? What's that equal to? Well, apparently mgh, right? And what's the kinetic energy at the top of the flight? 0, right? So 1/2 m times 0 squared. But anyway, this gives us what? This gives us, we can solve for v naught, right? We get v naught squared is equal to 2gh. What happened to the mass? Well, it wasn't given, and it doesn't matter, right? Because it divides out. And so what's our initial speed? Apparently, the square root of 2gh, which is what?
44.27.
44.27? That sounds right. Let me work it out here. 2 times 9.8 meters per second squared times my height, which was 100 meters. And it was rumored that this is 44.2. 4? Do you say 4? 44.27. Okay, 7, fine. Meters per second. So there you go. Is that easier than what we... this is definitely easier than the way we solved it before, right? But on the other hand, we don't gain information like how long did it take to the top, right? We had that before. Along the process of the calculation, we learn more, right? But this is a nice way of doing things. What is the timeless equation for the y direction, by the way? What is it? It's Vf squared, right? Equals V naught squared minus 2g change in y, right? That would be the timeless equation with respect to the y motion, right? Take that and consider this. If you multiply by 1/2 m, you get this. Well, what is that? Well, that's exactly 1/2 mvf squared, right? Plus m, there's a 2 here. My bad. There's a 2. Plus mgyf. So this is what I was just claiming, is that in fact the timeless equation is nothing more than the conservation of energy for the system in disguise. That's what it is. That's why it's powerful, the timeless equation, because it is a conservation of energy, really. Anyway, you guys have any other questions? Wait a minute, I didn't ask if you had any questions to start with, but how about now? I'd ask for comments, but I'm afraid. My college algebra class is fun this semester. They keep asking me various hypotheticals in terms of my love for completing the square. I was asked if I had a choice between ending world hunger and not being able to complete the square again, what I would choose. But it was stated in such a way that it was hypothetical for everybody, completing the square, not for everybody. I said, of course I would choose not to end world hunger, because completing the square is, well, if you can't complete the square, it's a world you don't want to live in. Because that's a world without mathematics, right? Then, like last time, they were stacking up my hatred of like mixed fraction notation, like 2 2/3 without the plus. I hate it. I hate it with a pure hatred. And they were asking me, did I hate that more than I loved the completing the square? That was a more difficult question. I still don't know. So, but they do ask interesting questions in college algebra, I tell you that. Anyway, so you guys have any questions? All right. Well, I tried. Example 2. How about this? Suppose we have a frictionless plane, because what other kind would you want, right? And you've got an incline, like so, at angle theta, all right? And suppose you give a box here, right, with mass m, a push at initial velocity v naught, all right? And whatever kind of annoying details there are about it going from like the flat part to the straight up part, we're going to ignore those. We're going to just assume it makes a smooth transition. If you want, maybe there's like a nice kind of like rounding kind of thing here, so it just kind of smoothly transitions up there. Okay, you got it? It's not going to fall over or anything funny. Question then, how high does it go? So how, let's see, like what distance up the plane does it go? Let me ask it the question that way, so it's at least a little bit interesting. How far does the box get up here? What's this distance? What's the max distance up the plane that the box goes? How would you figure that out? Again, we're assuming no friction for the moment. Don't worry, I'll bring friction back into it soon. I know you miss it. Taylor had an idea? No? No? All right. So I would say what's at play here is the only force really involved is gravity, right? That's a conservative force. Since there's no friction, energy is still conserved. All right? So I can still say, 1/2 mv0 squared, right, is equal to what? At the top here, at the highest point, intuitively speaking, what's the final velocity? It's 0, right? At the top of we're just before it starts sliding back down, right? It would be 0. So that should be equal to what? mgh, right? Plus 0. My point is there originally is 0 potential energy, and at the end there's 0 kinetic energy. Where did I put h equal to 0? By convenience, I put it here, right? Right there. So initially, I define the potential energy to be 0 at the start. I have this freedom to choose the potential energy to be 0 wherever I want. Although I can only do it once in a given problem. I can't make potential energy 0 two different spots in a given problem. That won't work. So then what? H isn't what I want. I want D. Can you figure out what H is? How about this? If I draw right here, this distance is H, right? My picture is not quite accurate. I mean, if we were doing things more carefully, I should be saying H is the distance to the center of mass of the box, all right? So I'm just being a little bit sloppy about that. We'll take care of the center of mass concept better as we go on in the course, but for the moment I'm ignoring, I never tell you how big these boxes are, do I? Right? How big is the box? I never said, because it doesn't matter. Until it does later in the course, but maybe never. So how do I figure out H? How is H related to D max? Can you tell me?
H is d sine theta.
H equals to D max sine theta. I think that's right. Yeah, that's right. So sine theta would be the opposite over the hypotenuse, right? And here that would be H over D max. So there you go. D max that we're looking for times sine theta. Well, that's my H, so I still have to multiply this by what? The mg I forgot to write, right? And check it out, the mass doesn't matter again, right? So yay. So the mass cancels, and we can solve for D max. What do we get? Let's see here, we get V0 squared, yeah, divided by 2, what else we got here? G sine theta, is that right? For reasons I don't fully understand, I woke up at like 2:40 this morning, and I started writing Calculus 2 notes, so I'm a little bit, So if I did an algebra mistake, I need to know about it, I think I got it. What do you guys think? Does this formula make sense? What happens if theta is 90 degrees? Does it make sense? What does the formula become if theta is 90 degrees? We get V0 squared divided by 2g, right? Sine of 90 is 1. I think that does make sense. If you look back at this equation over here, right? If you solve this for h, you've got V0 squared over 2g, yeah? Wait a minute, did I do that right? So yeah, these equations match if you put theta equal to 90 degrees, which makes sense because in some kind of stupid sense, if you could tilt the plane vertically, that would be equivalent to just throwing the box straight up, right? And so the equations match in that sense. How about when theta is equal to 0? Does it make sense then? What happens when theta equals, what sign is 0? 0. Division by 0? Generally frowned upon. But in the limit that theta goes to 0, this goes to infinity. Does that make sense?
Yeah.
It does, right? If this is a frictionless plane, it should just keep going and going. So, all right. Any questions, I think? Let's see here. Let me find another example for us. Maybe we should add friction to the mix. What do you think? How do you modify conservation of energy in the presence of friction? How do we deal with that? How does that work? You don't? Well, that's a fun answer. Let's see here. I've got this wet leaf example I should do at some point, I guess. Well, let me talk about friction here for a second. Oh, there's one other thing I can do before we get to friction. How about this? Suppose you've got a spring, and you stick a mass on that spring, all right, and you compress it. Compress spring distance x, all right? And then what happens is that mass, you compress the spring, and the spring is not attached to the mass, right? So what's going to happen is the spring is going to push the mass, right? And it's going to send it flying across this frictionless plane. And then what's going to happen is, well, since we like inclined planes, we're going to put one over here. And then the question is, how far does the mass go up the plane, given that you've compressed it a distance x over here, given spring constant k? How would you do this problem? Again, frictionless plane. So we could, and we could ask another question, which is how fast is it going just as it leaves the spring, right? Or I could ask this question. I could say, how fast is it going on the flat part, on the level part of the plane? Because if we're assuming that that plane is frictionless, it should be going with constant velocity along that the whole way, right? So as I think about this problem, there are kind of 3 steps, right? There is like step 1. There's step 2. There's step 3. So step 1 is the start. So there the energy is equal to 1/2 kx squared. So the energy at the start is 1/2 kx squared because we're assuming that it's compressed, it's not moving. The spring is not moving, right? So all of the energy is in the potential energy of the spring, which we worked out last class to be 1/2 kx squared, right? 1/2 kx squared would be the energy of the spring. So that's the energy at step 1. Now the energy at step 2, it would be 1/2 mv0 squared, right? So that would be after the spring stretches out somewhere in here, right? The spring gets to its like equilibrium. Once the spring reaches its equilibrium, right? Then the box just goes sliding with velocity v0 over, and it keeps sliding, right? And like I said, the spring's not attached to the mass. So once it gets past the equilibrium point, what the spring is going to do is just going to pull back, and it's not going to do anything more to the mass, and the mass just keeps going. So step 2, we'd have just purely kinetic energy, right? Again, I'm defining the h equal to 0, the gravitational potential energy, to be 0 on the flat part. And how about step 3? Once it reaches the max, what's the energy equal to? Well, mgh, right? But as we discussed, that would be mg d sine theta, wouldn't it? I guess I should give us an angle, huh? And energy is conserved, right? Because the only forces at work here are conservative. There's nothing taking away the energy from the mass. So we can just equate these and answer the question, right? So like, for instance, 1/2 kx squared is equal to 1/2 m v naught squared. So v naught apparently is, well, v naught squared would be kx squared over m. So my initial speed would be the square root of kx squared over m. So if I gave you some numbers for the spring constant and the mass, you could figure that out. Now the mass matters, right? The mass doesn't cancel out in this problem, because for a given spring, if you make it move different masses, you're going to get different velocities, right? If you have the spring push on a much larger mass, you're going to get a smaller velocity, right? Okay, so great. That gives me, that's the answer to the how fast on the level plane part. That's the answer to that. How far does it go up? So we can state it in terms of x, right? So the idea here is E1 equals E2 equals E3. So if I'm just interested in the relation between x and d, we can solve 1/2 kx squared equals to mg d sine theta. What would that give us? That would give me the distance up the plane is apparently 1/2 kx squared divided by mg sine theta. Or you could bring the 2 downstairs and write this in a more civilized way. There you go. D is equal to this. Here you go. That would be that. Let's work a problem with some numbers in it. You guys get uneasy if I use letters too much. So example 4. Suppose, of course, if you guys have a question, just jump in, you know. So, all right. Let's suppose that we have a mass initially sitting up here, all right? Well, my box is getting all squished. So think of it as an Amazon box. See here. So maybe you're at 30 degrees there. I'll give you a number. Happy? And then, and let's suppose that you're, I don't know, what's a good number? 10 meters. You're 10 meters up, all right? Your mass is, let's say, 5 kilograms, all right? Okay? And let's suppose that the coefficient of kinetic friction is 0.1, just to be sure I don't make something illogical. I'm pretty sure if we have a coefficient of kinetic friction of 0.1, it's going to be sliding from the start, right? Like let's suppose that the coefficient of static friction is 0.2. How could we check to make sure that it starts sliding and doesn't stay put? And I'm assuming that that there's that coefficient of friction on the inclined part and the flat part. All right. I'm going to ask the question: how far does it slide? Okay. That's the question we're going to ask: is where does the box get to, given this? So the first question to answer is: does it slide at all? How do we decide that? Energy doesn't fix that for us. That's a problem of forces, right? So we have to think about the free body diagram and what are the forces at work here. So you've got what? Your force parallel down the plane. You got yourself the mg, what is it, sine 30, right? And what's the normal force? The normal force would be mg cosine 30, right? So in this case, I can't. I poor planning on my part. There's Fn. Sorry, it's so tiny. But here's your mg cosine 30 down here, right? This is the same picture we drew many times. So my question then is, how big is the force of static friction? What's force of static friction? Max. Well, it is equal to mu sub s times the normal force, right? Which is equal to what? Well, I gave you it to be 0.2. What's the normal force? mg cosine 30. We can work that out. We've got numbers here. So 0.2 times 5 kilograms times 9.8 meters per second squared, still on Earth. And cosine of 30 is about 0.866, something like that. So what is my max force of friction available given the situation here? .2 times 5 times 9.8 times cosine of 30. I get 8.487 newtons. Is that enough to keep it put? What's this right here? This is the force pulling the box down the plane, right? So what's this equal to? You got 5 kilograms times what? 9.8 meters per second squared. Sine of 30, well, that's a half. So the parallel component of gravity in this case is (24.5 newtons). Ooh. So what does that mean? That means it moves, right? That is more than the static friction can provide, so it is sliding. All right? Great. Okay, so there we go. It's sliding. Okay, so here's how you work a problem like this. In this case, what we want to say is that we have our initial energy, right, at the start, right? It's equal to what? Well, it's equal to the energy at the end, you know, basically plus the work done by friction. That's not quite the right way to say it here. Sorry, I haven't said this correctly. Let me say it in a more natural way. Let me not say it that way. I told you I'm not quite right today. I mean, that's always true, but today what I should write here, to be more to the point, if we're asking where does it come to rest, right? Intuitively speaking, what's going on here is the energy at the start is going to be equal to what? The energy lost to friction, right? That's what's happening. Now, why does it have energy at the start? Where's the energy coming from? I said the box is initially at rest, right? So yeah, it's got potential energy due to gravity. So the situation here is we've got, you know, mg mgh is the initial energy, right? And how do you calculate the energy lost due to friction? So the good news is, in each case, right, if I draw a picture over here, right, the box is here, right? Where's the velocity of the box is like this, right? Where's the force of friction in that case? Opposite, right? So this is the force of friction, right? And then the same thing happens down here. My point to you is that the force of friction, the energy lost due to friction, you don't need an angle or anything, right? It's just the distance times the force will give you the work done by friction, right? In terms of magnitude. I'm trying not to say anything about sign here at the moment. So what is the force of friction here? On the sliding part, what's the force of friction? We have what? We have, what is the force? The normal force is what? mg cosine 30. So we've got mu k times the normal force, and then, you know, the distance down the plane, right? I need to give a label. Let me call this label, this distance d, right? And then plus mu k times the normal force. So this is on the plane, right? Inclined plane, I should say. What's the normal force once it gets to the flat, though? It's different, right? Here, the normal force is just what? It's just mg, right? So the normal force is bigger down there, which means the friction force is larger once we're off the mountain here. So I can just put mg here, right? And then I don't know what this distance is. I'm just going to call it x. Now I need to be careful. If I have made, well, I think it's going to slide all the way down. It's not going to stop it, I don't think. I mean, it's conceivable that the friction is large enough that in the process of sliding down, could it stop in the middle? Well, we'll find out. So what's d? 10 sine of 30? No. The hypotenuse should be longer than the opposite side. 10 over sine of 30, I think we'll do it. Yeah. So we've got, let's see here. My normal force was mg cosine 30, right? So there's an m everywhere. And in fact, there's an m and a g everywhere here, right? So let's divide by mg to make life easier. We have h is equal to mu k, and you guys just told me it was 10 meters over sine 30. I think that's right. So in other words, the hypotenuse is actually 20 meters. Yeah. So there's 20 meters to slide down if this is 10 and that's 30. I think that makes sense. Yeah, because 10 over 20 should be a half, which is sine 30. Good. And then mu k m, well, mu k x, whatever that is. All right, so my h was what? 10 meters, right? And that's going to be equal to 0.2 times, this is 20 meters, right? Plus, oh man. Oh wait, no, I spoke too soon. For a second there, I just saw the, I was thinking a half. I was thinking 0.5 times 20, and I was like, curses. See, if it was 0.5, it would have just got to the bottom and stopped there. Anyway, 0.2x. All right, so we can solve for x and find out how far it went. Oh, I'm bad. What was my mu k? It was 0.1, right? So I got to put 0.1 here. So what's this give us? It gives us 0.1x equals to, what's that, 8 meters? So apparently it's going to slide 80 meters. Follow-up question, how fast is it going just as it reaches here? Can you guys tell me? How fast would it be going? What's its V naught here? So we can kind of, once we know, if that 80 meters is correct, it's easy to figure out what V naught was, right? Because 80 meters is how long this initial speed takes to be lost due to friction. Yes, sir? Oh man, that's a good question. This is the danger of dividing things out without writing them. So I think I owe you I thought this worked out really nice, but yeah, it's wrong. So as you pointed out, there is a cosine 30 in here that I owe you that here, right? Thank you, Caleb. I do appreciate the correction. So that means, I gotta get my calculator. What do we got? Let's see here, cosine 30. That works out to the square root of 3. That's funny. I think, wait a minute, what? Uh-oh. I did something wrong. Oh, no. So I think I got 8 point, come on. Stupid. I need another hand. Why do we only have 2 hands? Let's see here. My wife has long held that one proof against evolution is that mothers don't have 3 hands or more. I mean, that's if you believe in the Lamarckian evolution, I suppose, but shouldn't you? After all, that's how they sold it to everybody. 8.268 meters is 0.1x. So we weren't far off, but I think it's 82.68 meters if I've not made a calculator mistake. Is that right? You guys get that? So how fast was it going before it slowed down on this flat plane? See, so if you work backwards, 1/2 mv naught squared, right? That's its initial energy, right? And it doesn't change potential energy going from here to here. So I can say that 1/2 mv naught squared is equal to what? The work done by friction, right? So it should be equal to 82.68 meters times the force of friction. What was the force of friction on the flat? Well, that's easy. It's 0.1 times the mg, right? This is the force of friction on the flat part. And so apparently, and that's meters, not mass. You know, it is what it is. Although the masses cancel now, which is nice. And we get that V naught is equal to the square root of twice 82.68 meters times 0.1 times 9.8 meters per second squared. What's that give us? If I haven't made a mistake, we have 12.73 meters per second. could also ask the question, how much energy did it lose? How much energy did the mass lose as it slid down the plane, right? You could figure that out by comparing how much energy did it have at the start? What would be the energy initially? mgh, right? So the initial energy was 5, I'm just going to work it out here, 5 times 9.8 times 10. So the initial energy is, in fact, 490 joules. How much energy does it have after it reaches right here? Well, how much energy is this? Well, it's easier to calculate over here, right? Because we already have those numbers. So, well, I guess I could do the 1/2 mv squared, right? So 12.73, square that thing, times the mass, which was 5, divide by 2. I get this is 405.1 joules. So how much energy did it lose to friction as it was sliding down the incline? You subtract these, right? So 490 minus 405.1, I get, it lost 84.9 joules in the process of sliding down the incline part. Are we good? Yes, no, maybe so, no? How could I change this problem and still make it reasonable? How can I make this problem easier? Yeah.
Take away friction.
Take away friction is true. Let me rephrase that question. How could I make this problem easier without taking away friction? How could I take away the initial, hey, is it really moving step? I just do what? Give it a shove, right? Give you the answer. I have long said that if we really wanted to fix S rates, we should have professors take the tests. What better way to improve the success rates in a course than to take the tests for the students, right?
Yes.
I mean, I think if I just devoted a half of my Saturday to take tests for students in math classes, I could vastly improve general math scores, you know? It'd be fantastic. It'd be just as meaningful as you know, judging the metric for success in courses as students doing electronic homework that's solved by Chegg means nothing. Anyway, that would never happen. Chegg is a studying website. It's not for cheating. I know. That's what the CEO of Chegg says, right? So it must be true. So if I give the box a shove at the start, then there's no issue of it's not moving or not, right? If you just shove the box and I give it initial speed, then we could work the problem without the initial, hey, is it moving step, right? That's a way to make this problem easier on the test, to do that, right? But what's the change then? The change is then the initial energy is not just mgh, right? If I give the box a shove at the start, then the initial energy would be mgh plus 1/2 m, the initial speed squared, right? And then you'd have to track that. But that's a usual modification of this problem. Let's see here. Whoa. Did I just end on time? By accident? I mean on purpose, as I planned. Enjoy your day. Oh, here, I have another idea. We have to turn off the video first though.